So far in our study of vectors, we have been talking about the individual forces represented by vectors that have been working on an object. So let's say a sled being pulled, it's being pulled horizontally, and if you're holding it in your hand, it's also being pulled up. The resultant then is the combination of those two forces working on the sled, and that's what we've been most interested in, okay? Finding that out. Sometimes it was in a right angle triangle, sometimes it was in a parallelogram. We had to organize our vectors either tail to tail or tail to head in order to help us find the resultant. And then at some points we were also interested in the equilibrant vector, which would balance the situation, creating a zero vector. So you can see that this is actually the force working that the sled is pulling on the person, you could say. Now, in this section, we're going to be going from a resultant vector, and we're going to be breaking it down into its rectangular components, into the two individual forces or multiple individual forces that are working on the object. Okay, so we're going to be given, instead of having, the sled is being pulled at 200 newtons horizontally and 100 newtons up, and finding the resultant, we're going to be given the resultant and finding the rectangular components. Okay, this is called resolution, or resolving a vector into two perpendicular vectors. So a vector, in this case, in the diagram, the vector r, can be resolved into two perpendicular vectors whose sum is the given vector. So if we're given the vector r, we can resolve it into two perpendicular vectors, which are the rectangular components, and the sum of those things is the original vector, which is what resultant really means. This is done, for example, when both horizontal and vertical forces are acting on an object, and these black vectors are the rectangular components of the force. So if we consider a vector r at an angle of theta to the horizontal, it can be resolved into rectangular components. This would then be, I don't really like that we're using r, but let's say I call it, because we're talking in terms of resultant, but let's say this was any vector, okay? Any vector v, okay? Then what we have is we have the vector v subscript h, horizontal force causing v, and we have v, the vertical force acting on v. So in our diagram, the given vector v is equal to vh plus v subscript v. Okay, the horizontal component and the vertical component add together to give us the resultant vector v. And you can see we have a right angle triangle that we're going to be using our trig skills again. All right, let's jump right into an example. Example 1. Okay, we're finding the rectangular components of a force. We have a tow truck, and it's pulling a car from a ditch. The tension in the cable, so cable tension, is 15,000 newtons at an angle of 40 degrees to the horizontal. All right, so we can picture this tow truck. We've got a car in the ditch and 40 degrees to the horizontal. So I'm going to draw my horizontal. Let's go ahead and do it in blue here. Here's our horizontal, okay? And at an angle of 40 degrees, we have a vector at 40 degrees of 15,000 newtons. Okay, so we have our horizontal drawn already, and there's our vertical. So to take the vector that we're given and to split it into its horizontal force and its vertical force is called resolving the vector into rectangular components. Okay, so we've drawn a diagram. We have all the information that we need. This is, we have a horizontal force, force H, and we have force V acting on the object, acting on the car in the ditch. And we can figure out what both of those are. So the tension can be resolved into two rectangular components, force vertical and force horizontal. And we are going to be able to use Sohcahtoa for this because we're in a right angle triangle. Essentially, we're finding the magnitude of this vector and of this vector, and we know the direction already. This one is horizontal and this one is vertical. So these problems, well, this one in particular actually ends up being a bit more straightforward because we don't need a direction because we already know the direction. So here we go. We are in a right angle triangle. I'm going to give us Sohcahtoa. We have the hypotenuse, and if we deal with the horizontal force first, then we have the adjacent and the hypotenuse. So we're looking at cosine. So we have the cosine of 40 degrees is equal to hypotenuse at the bottom. In the denominator, we have 15,000. And in the numerator, we have the magnitude of force H. All right, so that means if we're in a division triangle, the force H divided by 1500 equals cos 40. So the force of H then also equals 1500 times the cosine of 40, which is approximately 11,490. 11,490. All right, so that is the horizontal force, the magnitude of the horizontal force acting on the car being pulled out of the ditch. Now, same idea for the vertical force. This time we're looking at opposite over hypotenuse. So we have the sine of 40 degrees is the vertical force, the magnitude of the vertical force, over the magnitude of the vector representing the hypotenuse here. So the magnitude of the vertical force is equal to 15,000 times the sine of 40 degrees, which is approximately 9,642. Click that away in your calculator. All right, so we've taken this vector that we've been given of the tow truck pulling the car out of the ditch, we've split it up into its rectangular components, and we know the magnitude of the horizontal component measured in newtons, and the magnitude of the vertical component measured in newtons. Second example, we're going to find rectangular components that are not horizontal and vertical. Okay, so we have a situation where a box is on a ramp. So we have a box, and it weighs 140 newtons. It's resting on a ramp, and the ramp is inclined at an angle of 20 degrees. Okay, so those are the two things that we have. And we're going to resolve the weight into rectangular components that is keeping the box at rest. Okay, so the box is being held at equilibrium by two rectangular components, two forces. I'm going to draw a diagram here. It's going to help us understand it. We're going to take this diagram and then eventually split it up into other diagrams as well. But to start, we have a ramp. Okay. we have an angle of 20 degrees here, and we have a box. And we're told that the box is at rest, okay? So let's talk about the forces that are acting on the box. Well, we know that gravity is pulling it down, and that's given to us by its weight, okay? So right away we know there's a force pulling down on this thing that is 140 newtons. The box is also, there's friction between the box and the ramp. So friction is holding the box from going down. If there were no friction, then this downward pull would end up pulling the box down the ramp. So there's enough friction that's holding it in place. Now friction acts parallel to the ramp, okay? So what do we have so far? We have the force of friction acting on this, and we have a force of weight pulling straight down. Could be a little bit more straight down. Okay. And now what we need to do is understand that there is another force stopping. So friction is not enough to stop it from coming down. There's another force, and it's acting, and it is in relation to the ramp, okay? So what happens when you're on a ramp is that the other force acting on it is perpendicular to the surface of the ramp itself, okay? So this is an unknown force perpendicular to the ramp. It's the natural effect of putting something on a ramp in physics. That means it's not falling straight down, right? It's not just able to go zoop, done. There's something in its way. It's this ramp. It's restricting the vertical force pulling on the box due to gravity, okay? That's what this vector represents. So we have that force, just the existence of a ramp, even if there were no friction, okay? The ramp would restrict the pull of gravity on the box. That makes sense because it can't fall straight down, because it would, if there were no friction, it would slide this way, okay? Now, we also then have, on top of that, we have friction, and those two forces combined are holding this box at equilibrium, okay? So what we're looking at then is what is the combined force of these two vectors, vector f and vector n. So what we can do is we could take, and you can notice that, look, they're at a right angle there, okay? And so I could leave it here. I drew my diagram kind of big enough, but I'm gonna just take it over here. There's vector n. There's vector f. They meet at a right angle. And I drew this vector wrong again. It's pulling down. The ramp is holding it up, right? The ramp is holding it up. So just quick erase those. Yeah, I got to think through every piece, make sure what you're doing makes sense. And now I can see I have my the sum of these vectors, the resultant, just completes the right angle triangle with a hypotenuse here. And my goal then is to find out what this vector is, okay? And actually, it's not to find out what this vector is. I know what this vector is. It's the vector that ends up holding up this 140 newtons. It's going to cause equilibrium, right? We said this vector plus this vector causes equilibrium. It causes the box to stay at rest. It balances out the force of the box itself wanting to come down. Okay, so that's an upward vector, 140 newtons. And from our diagram, due to like parallel lines and lengths and things like that, we actually know that this angle here is 20 degrees. All right. So we have a right angle triangle, we have a hypotenuse, and we have an angle, which means that we can use Sohcahtoa in order to determine the magnitude of f and the magnitude of n. So we're going to do that now. The magnitude of n is equal to 140 over the cosine of 20 degrees. So if we have Sohcahtoa, Sohcahtoa, may as well write it on the top of every page. And we have the cosine of 20 degrees is adjacent over hypotenuse. So then adjacent is the hypotenuse times the cosine of 20 degrees. So we've got 140 times the cosine of 20 degrees, which is approximately 131.6 newtons. And then for our friction vector, the magnitude of it, that's going to be 140 times the sine of 20, because we're dealing with opposite and hypotenuse, which is approximately 47.9 newtons. Okay, so the box is kept at rest by a force of 131.6 newtons perpendicular to the surface of the ramp, and by a friction of 47.9 newtons parallel to the surface of the ramp. So non-horizontal and vertical, but still rectangular, okay, with this right angle triangle. And we could maybe, I'll put the direction in here as well. So it's kept at rest by a force of 131.6 newtons perpendicular to surface of ramp, and 47.9 newtons friction parallel to surface of ramp. All right, that's it for lesson 6.5, short and sweet. Practice problems are found on page 349, and you should be able to handle 1 through 15. Thanks for watching.